Hello, this presentation is about an idea called wandering threads that lets you do SMP style programming on NUMA architectures. It provides a way to get better performance and security with legacy code. For many years we've used machines with magnetic hard drives, DRAM and caches. The DRAM is used for virtual memory and swaps in and out to the magnetic drives. The cache is generally a small fast memory close to the processor. As you can see, the speed varies depending on the distance you go from the processor. A modern processor is pretty much the same as the older processors, except we have more cores and more memory, and now we have solid state memory instead of the magnetic drives of before. The SMP architecture relies on a common data bus. Each processor can see all the memories, and you may as a result get contention for the bus as data goes back and forth. The common bus is required for cache coherency across the processors. Ideally, we'd like to cut the bus between these processing units so that we don't get the contention and each unit can go full speed all the time. In the new architecture, any time a thread tries to access data which is not local to the processor it is on, it will be transferred to the processor most likely to have that data in cache. Threads can be moved by a variety of mechanisms, the main goal being to avoid them colliding while they're moving about. From the programmer's and compiler writer's perspective, the computer is basically a Turing machine executing individual instructions one at a time in a long sequence. The wandering thread machine looks pretty similar to the regular Turing machine, except we're inserting extra sequences to move threads around between CPUs. Here we have a simple routine that's accessing memory. This may be across CPUs, and we might want to move the thread. The problem is it's quite difficult to identify the move instruction that does that, so we back off from the move instruction to the call to the routine that has the move instruction, because it's easier to insert code at the call boundaries for the routines. And the ABI is invariant with the style of code used, so it's much easier to identify the behavior at the call boundary. Here we have some example shim code which is inserted to decide whether to move the thread or not. The code looks at the arguments to the original call and tries to work out whether local or remote. The thread will move to the location of the first argument, and then maybe the second if they're in different memories, before finally calling the original call with local data. The WT transfer call you see in the code will move the entire context of the function to the new processor. That may include locally dereferenced data. Local context data is expected to move from L1 cache on the first processor to L1 cache on the second processor, avoiding the data buses. Threads that are being moved to the same processor can be serialized at the call level. That avoids inappropriate interleaving of data that you sometimes see at lower levels. Single-threaded performance improves with wandering threads because the threads are working out of cache most of the time. And moving a thread is half the time it takes to ask for data and fetch it. Parallel computing performance improves because we don't have contention on data buses, and threads can wander around not colliding with each other if there are lots of cores. Moving threads to the same processor for a given piece of data means that the requirement for coherency across all the caches is much lower. And that allows you to remove some hardware from the chips. Within an existing application, we can be smart about how we allocate things into memory. That allows us to segment where the processing is done to, so one processor's data is not available to another's, and threads are therefore not able to snoop each other's data. The wandering threads approach would work for SMP hardware as well as new hardware. The minimum approach in implementing something is to just modify the linker and hand code the shims for your particular application. Anything with large amounts of static data should benefit. Database search and simulation are two cases that spring to mind. Beyond the linker modifications, LLVM can be extended to add the context wrap up for moving the threads about, and also to generate the shim decision code automatically. In the case of C++, we expect to generate multiple versions of method code, and to be able to dynamically change which set of methods are being used according to the set of data that we're currently dealing with. That minimizes bad branch behavior and lets you eliminate some of the branch prediction hardware. At the hardware level, the approach can be enhanced by adding shadow registers that will tell the decision code very quickly whether things need to be moved or not. Other hardware can be added for moving threads around. It could be FPGA, fabrics, or any kind of network communication hardware that you already have. Since processors work fastest out of cache, and getting a lot of cache in place means getting a lot of cores in place, especially if those cores are low power. Asynchronous processors are the lowest power processors. Due to the high variability in silicon down at the FinFET level, asynchronous processors are actually likely to be faster anyway. If you turn the voltage up on them, they're going to be very fast, and they'll run hot, but if the threads are moving all the time, they don't stay hot for long. If your processors are running cool most of the time, then it's fairly easy to die stack them with other technologies like flash memory or 3D crosspoint